sign up with it? Everyone?
Yep. Probably going to try to say that day or two.
Okay, so I'm going to begin here. First, let's go through some logistics that I think are going to be important. So it looks like quite a few of you have already found the this Google Doc, which is a sign-up sheet for when you want to present a journal article to the group. I'm glad that someone decided to take the second one. I figured I'd have to pull teeth to get that to happen, but thank you very much for doing that. So anyhow, so this is the schedule. Again, remember that this is part of your class participation points, is signing up for one of these. And I'll be doing the first one, which is, I guess, a week from today is what we're doing the first one, to kind of give you a sense of how this will proceed. And then from there, the students will take over and present some subsequent journal articles to the group, and we'll talk about them. So thanks for everyone who signed up for a slot. For those of you who haven't, please do so before you get stuck in that you don't want to have. Other things to talk about here. We have the first homework assignment, like I said, the last class has been posted, so you can take a look at this. Again, this is all to be submitted online, so so do not like drop by my house at midnight on September 7th expecting to turn this in. This all goes on Carmen online. The first homework set is probably easier than all the rest of them are going to be, but it's going to be going through some of the basics of ODEs, PDEs, and starting to get into applications that we'll look at in this class. So you can take a look at this. First homework assignment, again, remember you have 3 weeks to do it, so start early on this homework assignment. If you go to Carmen, you'll see some of the information in terms of academic integrity. This is reflected in the syllabus as well, but each homework assignment will give you kind of the parameters. You're in graduate school. You work on projects collaboratively with other people in your research group. You probably worked on homework assignments collaboratively as undergrad as well. The same applies here. I'm available for help. By the end of today, I'm going to go check the doodle poll and see when the best time is for office hours. So please stop in at office hours if you need help. But the goal here is for you to, by the end of a homework assignment, really understand the homework assignment, not necessarily just to grade you, right? The goal of the homework assignment is to build understanding. Okay, I think that's it for logistics. Oh yeah, the other thing with logistics, I realize actually just now that I'm not sharing the files here, but I'll give you an idea of what the file structure looks like, and I'll make sure this is published so everyone can see this on Carmen. But we have, say, for instance, today we're going to go through Module 2. So Module 2 has PowerPoints, and getting into Module 2, you'll see that some of the slides have a significant amount of blank space in them. Okay, so what's going to happen is during today's class, I'm going to fill in the blank space. Okay. So if your preferred learning style is you want to have all these printed out in advance and fill in the blank space yourself, go for it. But in today's class, I'm going to fill in the blank space. I'm going to save that too, so you can have that document, and that's going to be posted to Carmen. There's going to be the video of me filling it out live. However you prefer to take in the information, it's up to you. If you prefer writing your notebook and then kind of transposing on these slides, that's up to you as well. So however you prefer to do it, all this information will be provided to you by the time by the end of today, right? Also in here, and I haven't uploaded it yet, but getting into some of these examples, for instance, there are plots of the end result after we solve a differential equation, because this one's about review differential equations. So all the code to produce these plots will be in this Carmen folder as well, and this is going to be probably most helpful in things you may not have seen before in terms of how do you make a plot that looks like this, a video, which is going to how we're going to quite often be looking at the solution to PDEs, because it's difficult to plot a PDE on a static screen sometimes, or the solution to PDE on a static screen. So code that will show you how you can turn basically a set of evaluations of functions into videos will be given in the file as well. Okay, any questions about some of those logistics things? Okay. And I'm just learning how to use this thing, and so my handwriting may be a little sloppy, and it may get better by the end of the semester. So. Okay, so before we get into actually additive manufacturing, I thought it'd be good to go through a review of ordinary differential equations, partial differential equations. How many of you had a class in PDEs as an undergrad or in graduate school? Okay, so about half the room, a little more than half the room. Okay, everyone should have had ODEs in undergrad. That's a kind of bread and butter of undergrad. But the way in which we're going to describe heat transfer, fluid mechanics, and additive manufacturing requires solving PDEs. We're not going to be going through a full treatment like you would get if you were to take a graduate class in PDEs in the math department. We don't have time to do that, but I'm going to go through some of the important solution methods that people have been able to use for additive manufacturing and give you kind of the base knowledge to solve fairly simple PDEs using methods called Green's functions, and then we'll show how this can be used to additive manufacturing problems. But before we get into PDEs, we'll get into something which I hope is a little bit more familiar, which is ODEs. Okay, and so this is the general form for an ordinary differential equation, right? So you have here, you have a derivative with respect to time. This can be derivative with respect to x. If this is, if all these are x, but it's an ODE because basically every single derivative here is with respect to time, right? So you have a second derivative, or first derivative with respect to time. Second would be here all the way up to n derivatives with respect to time. This would be an ODE. This is what we call sometimes the non-homogeneous term, or a forcing term, or exogenous term in our ordinary differential equation. If we consider the homogeneous case, right, which means that g of t is equal to 0, then this nth order ODE, right, because we have n derivatives in it, is going to have n linearly independent solutions, y1, y2, all the way up to yn, right? And we can anticipate what a solution, that a solution is of the form y is equal to e to the rt. Right? And so the reason why we can do this, we can just say, consider the simple case of y primed plus ay is equal to 0. So if we assume that y is equal to er of rt, the exponential function is one of those very unique functions that if we take the derivative of an exponential, we get an exponential back, raised to the same exact power, right? So if that's our differential equation, then we have then y primed is going to be equal to r e to the rt. For some reason, I don't know why that little line showed up. Okay. Plus a e to the rt is equal to 0. So if I say that r is equal to negative a, then we see that we get negative a e to the negative at plus a e to the negative at is equal to 0. And so our differential equation is satisfied, right? So with ODEs, all of our solutions are always going to be the form of y is equal to e to the rt. That's just well, I guess I should say, for constant parameter linear ordinary differential equations, we'll have this case here. All right, so this should be review here. Moreover, there will be n unique solutions for r. So if we look at and say that again that y is equal to the form e is equal to rt, I could rewrite this equation here as e to the rt parentheses a naught r to the n plus a1 r to the n minus n minus 1 a n minus 1 r plus a n is equal to 0, right? All right, so that's just looking at every time we have a derivative, we have an r to that order of that derivative pop out, right? And so then we can say that the solution to this differential equation, we have to have r's such that z of r is equal to 0, where this whole term here is z of r, right? So this is an nth order polynomial, so then we can find n roots to this nth order polynomial, and that would be all of our linearly independent solutions, y1, y2, all the way up to yn. Okay, so quick example with this. right? So we take this pretty simple differential equation. Here I'm going to get e to the RT, r squared plus r plus 1 is equal to 0, right? If I want to solve this, so then this means setting this equal to 0, then I get, just using quadratic theorem, I would get this solution, right? So that means that r has two values, right? So we have a second order differential equation. R has two values, and the two values of r are negative 1/2 plus square root of 3 over 2i, negative 1/2 minus square root of 3 over 2i, right? So I'd say that y1 is equal to this function, then y2 I'm getting better at writing with this thing already. Is equal to this, right? Any questions about that? Okay. Okay, so then that was the differential equation without initial conditions, and you should recall that if you want to actually solve the unique solution to a differential equation, you have to know what the initial conditions are. So for an nth order differential equation, we need to know all your initial conditions for y naught, y primed, all the way up to y to the n minus 1. We have to have all those initial conditions to solve this. Just one note, I've already switched to this shorthand, but you should be familiar with this. When we say y prime, we always mean taking the derivative of our solution with respect to time. Right? And I'll get into partial differential equations how we're going to differentiate between partials with respect to space, but this is a pretty standard convention. Right? Okay, so for the homogeneous ODE G of t, the full set of initial conditions, there's only one unique solution. It's going to be of the form y is equal to c 1 e to the r1 t plus c2 e to the r2 t it's going to be of this form. Okay, and so all these C1s, these are all, all these C terms, these are all unknowns that we're going to have to solve for to then satisfy the initial conditions given here. Right? Okay, so an example. So pretty basic differential equation. Find the solution of y double prime plus y is equal to 0 for these initial conditions. So this is exactly the same problem that we just gave in example 2.1, but the only difference here is that we have initial conditions that we have to satisfy. So from example 2.1 and then the latest piece of information I just provided to you, we know that y is going to be of the form c1 e to the negative 1/2 plus square root of 3 over 2 I t plus c2, and then its complex conjugate in terms of the term in the exponent. So many of you probably saw this of a different form when you took this as undergrads. You probably saw this in the form of if you saw a solution to R that is complex conjugate, meaning it has a real part and an imaginary part, you automatically assume that the solution is the form cosine sine. Is that correct? Is that how most of you saw it? Okay. So this is exactly the same, it's just in exponential form. And I'll show you how it's exactly the same. I'm showing you this way because when we start to solve PDEs, you should get very, very comfortable with functions being in the form of exponentials, and we'll see that all the time. So this is just using the Euler identity to solve this. But we can start to look at these initial conditions. We have initial conditions of y is equal to 1, and y not is equal to 1, and y prime not is equal to 4. And so we get our first evaluation initial condition, y is 0. Okay, so if we look at this term right here, we have t is equal to 0, right? So e to the 0 is equal to 1. So we have y1, or y naught, is equal to c1 plus c2, with the same argument here, if we have t is equal to 0, right? Exponential raised to 0 is 1. If we look at what is y primed, okay, so I'm going to take the derivative of this function with respect to time. That's going to give me c1 negative 1/2 plus square root of 3 over 2i. And then this is going to be e to the whatever's in here, evaluate at 0. And so this all goes to 1, right? Next term, c2. And by the same argument, this is going to be e to the 0. So this goes to 1. Right. So I have these two relationships. I have two unknowns, c1 and c2. I have two equations. I can solve for this. So the handwritten notes that are all actually already posted on to Carmen goes through all the steps to solve for c1 and c2. This is just linear algebra, two equations, two unknowns. You solve for these two, and so if you were to go through and do this, you would get that c1 is equal to 1/2 minus square root of 2. Mistake. This is minus 3/2 square root of 3i. And then we get c2 is equal to 1/2 plus 3 over 2 square root of 3i would be our two solutions for c1 and c2. Okay, so plugging this back into our solution, we get y is equal to 1/2 3 over 2 square root of 3i All right, so that's the C1 e to the R1 term. Okay, so solution. Now we need to get this in the form of something that it looks more familiar to us. Sorry if I got rid of that too fast. I'll hold on to that for a second. Okay. So the way in which we're going to solve this is we're going to use Euler's identities, basically Euler identities. So we have these relationships. Cosine theta is equal to 1/2. I don't know what this little horizontal line is. E to the I theta plus e to the negative I theta. This is Euler identity. For cosine, Sign, very similar, but a little different. Is this right here. So you should get pretty familiar with working in this, going back and forth between cosines and then exponentials raised to imaginary numbers. Again, if you go through and apply this conversion, you'll get the solution to our differential equation is y of t is equal to e to the negative 1/2 t cosine square root of 3 over 2 t plus 3 square root of 3 e to the negative 1/2 t sine. Okay, so we'd have to apply then Euler's identities to our solution in forms of the coefficients on the exponentials being complex, having both a real part and an imaginary part, and you'll get this solution right here. Of course, you always want to test initial conditions. So if we look at initial conditions for this, evaluate this at y is equal to 0. The sine term, sine term here for time is equal to 0. This goes away. Sine of 0 is 0. Cosine term, cosine 0 is 1. E to the 0, 1. So why not satisfy? Y prime to 0. This is going to take a little bit more work, but you basically have to use the product rule for taking derivatives. All right, so I would get, for instance, I'll just start this. I won't finish it. The full one is in the notes, but I would get negative 1/2 e to the negative 1/2 t cosine square root of 3 over 2 t minus square root of 3 over 2 sine, right? Okay, so I'm missing the derivative of this term here, but for the sake of brevity, we would then evaluate this as y is at 0, and we would get 4, which is what we should get, given our initial condition was y prime to 0 is equal to 4. Okay, any questions about that? Okay, so I guess I'll go back to the form here. If you'll notice the relationship, I think this is one of the more important things to point out here. If we go back to this slide here, we had our two solutions were the form negative 1/2 plus square root of 3 over 2i and all by t, right? And same thing with y2, except you just have the complex conjugate and the exponential. Right? So it's important to note that the real part is always going to end up being your decay term here, right? So the real part always becomes the decay. The imaginary part always becomes the frequency of your harmonic term here. Okay, so if we look at then the solution here, this is the solution. This is initial condition of y of 0 is equal to 1. Y prime to 0 is equal to 4. We'd have to kind of approximate what this derivative looks like here, but this would, if I extend this on, just by the best of my drawing, this is about a derivative of 4, approximately, with my crude drawing here. But this has the right initial conditions, but you'll see that then the period of this oscillation is 2 pi square root of 3 over 2, right? So this is the harmonic part. We said that the imaginary part of our solution was square root of 3 over 2. This directly influences the period of our oscillations. The decay is a decay at a rate of negative 1/2, or a time constant of 1/2. All right, so that's the most important thing to take from this solution is that real part of the solution to our characteristic polynomial, z of r, is the decay rate. Imaginary part is the frequency of oscillation. Here. And so then we can look at the general solution to constant parameter linear ordinary differential equations, and we can start to draw a map here. So if we say that we have a characteristic polynomial, and the solution to that characteristic polynomial, or for those of you who have taken controls classes in undergrad, you probably refer to these as poles. If you've taken state space system dynamics classes in grad school or in undergrad, you may refer to these as eigenvalues. But if we say that we have a characteristic polynomial or an eigenvalue or a pole on the negative real axis, we know that we're always going to get solutions of this form. Okay, for some reason I'm erasing this. Okay, so this is a pole that's fairly close to the imaginary axis. The solution is going to decay. I don't know why this is doing this. Okay, I don't know why it's doing that. Okay, just taking a delay for some reason. So the solution is going to decay without any oscillation in it. And that's because the imaginary part is 0, right? So there is no harmonic term in this function here. If the characteristic polynomial, I solve it, and instead that pole or eigenvalue is way out here, the solution is going to decay faster. Right? And that's because my e to the negative some term t, that some term is going to be a larger number. So my decay is going to be faster here. Alternatively, if I look at a characteristic polynomial where the solution is in the right half plane, I'm going to get this response. That's going to be e to the positive number t. Those functions explode in time. Right? All right, so those are having real solutions to your characteristic polynomial. If we look at ones that are purely imaginary, all right, so if you have a, say, plus, I don't know, we'll call it 5i term, you always have to have a negative 5i solution to your characteristic polynomial, right? So it's a complex term always has a complex conjugate when we solve polynomials. So this would be solutions that oscillate and never decay. So the real part of this solution to the characteristic polynomial just is 0, so this just continues to oscillate, right? So never increasing or decreasing, it just continues to oscillate. If I look at now combinations, say my characteristic polynomial has both a real part and an imaginary part, I get a combination of the two. So I have the same decay envelope profile, I have the same frequency, and so I'm going to get solutions that look like I don't know why that doesn't work. This. So decay profile is approximately the same frequency, but this, I think, without having to solve the differential equation full out, you can actually get a really good sense of how the solution is going to evolve just by looking at the solutions to the characteristic polynomial. So this gives us a map that as our solution to our characteristic polynomial moves in this direction, we get increasing explosion rate. If I say explosion is a function that goes off to infinity, as my pole moves in this direction, this would be increasing decay rate. All right. And then as the complex conjugate poles move farther away from the real axis, this is increasing frequency. Any questions about that map? This is going to be pretty important when we get to the latter half of this semester when we talk about systems integration control. Has everyone seen this before? Anyone that has not seen this? Okay, so thus far we've only talked about homogeneous ordinary differential equations. There are also non-homogeneous differential equations. So by non-homogeneous, we mean that we have some sort of non-homogeneous term. So what makes this term different? It's not a function of y. Y is our solution to this differential equation, right? It's a function all by itself. This is an exogenous term or forcing function, called that way as well. So a non-homogeneous ODE, it means g of t is not equal to 0. The full set of initial conditions can be solved by the method of undetermined coefficients. There are also other methods as well. We're not going to go through those, provided that g of t is in some sort of simple form, right? So these simple forms actually encompass a lot of practical problems we will see in this class and in engineering in general. But say, for instance, g of t is a constant, g of t is a ramp function, decaying exponential, cosine, etc. Okay, so our solution is going to have two parts. Y of t is going to be equal to the homogeneous solution and the particular solution. Okay, so the homogeneous solution is essentially what we solved on example, whatever that was, 2.2. And now we have cases where we want to solve the particular solution. So this would be an example of a non-homogeneous ODE because we have some sort of driving function cosine here. So leveraging exactly the same left-hand side or homogeneous part of this differential equation, so we can leverage a lot of the work that we've already done before, exact same initial conditions that were selected as well. So the only thing different here is now we have a particular part of our solution we have to consider. So YH of t, the homogeneous solution, we already know this form. All right, and then our particular solution by methods of what it's called undetermined coefficients. I'm blank for a second. If we have a cosine function, we always assume we have a cosine and a sine term. And there are a bunch of rules on how to properly do this, which I'm not going to go through all of this in this class. But our particular solution, we're going to assume is in the form of C3 cosine square root of 3 over 2 t. Oops, that's a 3. Plus C4 sine square root of 3 over 2t. Okay, so given this assumed solution, we can then look at higher order derivatives. We want to basically plug this back in to our differential equation and make sure it's satisfied after the homogeneous part of the solution dies out. So we can look at y primed of t, y primed of yp of t prime, right, is going to be equal to negative square root of 3 over 2 C3 sine square root of 3 over 2 t plus square root of 3 over 2 C4 cosine. Okay. So then the next derivative of this is basically going to follow the same exact form. Oops. Okay. All right. So what we're going to do is we're going to plug yp, y primed, or sorry, yp, yp primed, yp double primed back into our differential equation here, and then solve for unknown coefficients here. Okay, so this is substituting everything into the left-hand side of our differential equation. This is now the right side. Okay, and what you'll see is that we have a bunch of terms that have coefficients of cosine, and a bunch of terms that have coefficients of sine on them, right? So again, just like before, we had initial conditions. We have basically just a linear algebra. We have now equations in cosine, equations in sine. That gives us two equations that we can solve. We have two unknowns that we can get C3, C4. C3, C4, what are those? Oh, there they are. Okay, sorry. So skipping all the work to get to this, this is in the notes. This is going to be 4 over 13. C4 is equal to 8 over 13 square root of 3. And then what you can do is you can go, so once we have this, we can then look at the entire solution, which is going to be that y. Lost? Or student lost or what? I don't know. Okay. All right, so you have a particular solution which we have essentially solved for already because we solved for C3 and C4. We have the homogeneous solution, which doesn't yet have the coefficients determined yet, which we can go back and figure out those just with the exact same methods that we did in the previous example, and we get the entire solution. So the entire solution is fairly long, so I'm not going to write it out, but I wanted to point out some of the fundamental features here. So we have particular solution, which is in the form cosine and sine. So that is this dot dashed line here. See that this is sine and cosine. This is just staying as a sine and cosine always. It never decays, it never increases, always stays the same. That obviously would not be the case if your driving function is an exponential or if it's a constant, it will stay the same as well. The particular solution, or the homogeneous solution, decays. And that's because we have, in our homogeneous solution, we have e to the negative 1/2 t terms in it, right? So as time gets very, very large, it gets e to the 0, or e to the negative large number, which is going to 0, right? So that term decays. The actual solution is this blue line, and that is the summation of the two. So you can see that this satisfies the initial conditions in terms of both position and velocity. And then at time getting large, it converges to a harmonic function that is the same as our driving function, right, which is square root of 3 over 2 in terms of its frequency. Okay. Any questions on that example? Okay. All right, so that's one way to solve differential equations. I think the one that you're probably most familiar with. There are also other methods that are actually going to be quite valuable when we get into PDEs. And so I wanted to show you those. And that's what's called a kernel solution to your differential equation, or what's called convolution. So you may have seen this in a system dynamics class or controls class if you took that as an undergrad or a graduate student. But kernel solutions are how we're going to look at how we solve PDEs. The ODE is just a particular case of PDE when you have a kernel solution to it. Also called a Green's function solution. So kernel methods, if you can consider going back to a simple differential equation which we had before, say for instance this differential equation with this initial condition. One solution to this is I guess we'll start to manipulate this a little bit here first. Okay. So if we multiply both sides by e to the negative at, and this may not seem logical yet, but we'll get to why this may be logical. Okay, so that's just multiplying both sides by e to the negative at. That's an allowable mathematical manipulation. And then we can use just the fact, d dt of e to the negative at y of t by the chain rule is equal to negative a e to the negative at plus e to the negative at y primes. So we have this fact. We can then substitute this back in, and we get, so this is, I'm missing something here. Sorry, my notes are missing something. This should be, I'm missing a y here. So this is this left-hand side right here, right? So I can substitute this back in. So that means the left-hand side, in fact, is equal to d dt e to the negative aty is equal to then our previous left or right-hand side g of t. And then if we integrate both sides of this, we get then the solution, not the solution yet. So integrate so I use the integrating factor tau. Okay, so I just integrated both sides with respect to tau going from 0 to t. And what that allows me to do is I can rewrite this differential equation here. I'm going to have to jump to the next slide. I can rewrite this as this function. So then doing a little bit of rearrangement, I get my solution is y of t is equal to e to the negative a t y naught plus integral 0 t e to the negative t minus tau b g of tau d tau. So I think I had, sorry, this is, so sorry, it's e to the positive t minus tau. And then, sorry, this is positive as well. Okay. Okay, so what this looks like here, this is in a different form than how we saw with the previous solution of the difference equation. So we have, this is going to be now our homogeneous response for a system. All right, because this is a function of our initial conditions, right? This is just a single, this is just a first order differential equation. This is extensible to higher order differential equations. That's a longer discussion that you would see in the linear systems class. But I wanted to point this out because this is going to be important when we get to partial differential equations and solving them with kernel methods or Green's functions. But this is our homogeneous response to our system. This is our particular solution here. All right, and it's a particular solution that it has our driving function in it. To solve this, you're solving what's called convolution, essentially. And we'll get into an example of that when we actually get into PDEs, and I'll show you this. But the main thing to point out is that this works for any constant parameter linear ordinary differential equation. Even higher order ones, we'd have to then turn this into a vector or matrix expression to get this to work. If we're doing higher order differential equations, this is a different way to solve these type of ordinary differential equations. Who has seen this before? Nate, in linear systems class? Yeah, okay. All right, so I'm bringing this up not because we're going to do a lot of this work for ODEs, but we're going to be doing this for PDEs for a lot of our solutions. It's going to be important for a lot of the really fundamental work that went on in additive manufacturing of this solution. I think this is a good time to take a break because next thing we're going to get into PDEs. So we'll take about a 5-minute break to let people stretch, relax their mind, etc. So we'll start again at 9:55 then. All right, let's start back up again. Actually, if I had to rewrite this slide, so right here I have this kernel solution is applicable to any integrable e to the negative, so e to the a t minus tau b g of t. So that's true in terms of having like a closed form solution for this. What's also important to point out here is that you can use numerical integration to solve this as well quite easily. And so even though this class is not about numerical methods, et cetera, these are existing tools that are pretty easy to do in a MATLAB script. Okay, so this is, especially with when we get to PDEs, we're going to have equations of this form. That's not really a numerical method in terms of thinking of a finite element grid, but we're going to use solutions like this, such as like trapezoidal integration that can do this quite easily for us. Okay, so PDEs. So I already asked this question in terms of who has had a course in PDEs, or I don't know, maybe not a whole course, but have seen PDEs before in some of your classes. For those of you not, this will be a little bit of a tough jump, I think. PDEs are considerably more difficult to solve than ODEs. And so since this is not a course in PDEs, we're going to be going through only the methods that are needed to understand additive manufacturing systems. And so this is the first time I'm introducing PDE methods. We're going to have to, as we get to content that needs a new type of solution for PDEs, we'll then do a review or introduction there. So everything here is building up for the very first parts of this class, which is trying to understand heat transfer for powder bed fusion is the first thing we're going to do. All right, so for those of you who had a PDE course, I hope this is a good review. It's not going to be as rigorous as a PDE course you take as a graduate student in the math department. Even if you have, you may have only learned one method, which is the most common one, which is separation of variables. And we're actually not going to start there at all. We're actually going to start with Green's function solutions, which are very similar to the kernel solution for ODEs that we just went through. All right. Okay, so first off, some kind of notation or terminology. This would be an example of a PDE. This is what's called the diffusion equation. So those of you who take a PDE class have probably seen this before. So our solution here is U, and we're saying that the partial of U with respect to T minus K, this is our diffusivity of our diffusion equation, times the second partial of U with respect to X is equal to 0. This is a standard diffusion equation. You'll find this in any PDE textbook you'll ever find. This is probably one of the most common ones, this in the wave equation. We can specify the domain then on X and T. So this is a single dimension in space, X. So in contrast to an ODE we typically only look at time here, and that in terms of a domain. In a PDE, we have to consider the domain in space as well. ODEs have initial conditions, but they don't have boundary conditions, right? So PDEs, we have initial conditions. This is our solution, U, as a function of X, evaluated time is equal to 0, is phi of X, right? So this would be the initial configuration of this function U in X. And also we have boundary conditions that we can specify. So we can say our boundaries in X are between 0 and L, and U at 0 is equal to some sort of function, U at L is equal to some sort of function in time. So this would be how we'd specify the standard diffusion equation in terms of a solution. We'll use shorthand here. This is common shorthand you'll see in any, or I guess most textbooks as well. If we say U underscore T, or U sub T, which we mean the partial of U with respect to T, and then likewise, U sub X would be partial of U with respect to X. U sub double X would be second partial of U with respect to X. Okay, so any solution has to satisfy these three things. It has to satisfy the PDE itself, has to satisfy the initial conditions, and it has to satisfy boundary conditions. We'll get into boundary conditions and the different types of boundary conditions in a second, but I'll go through a simple example first. So first, before we get into solving this problem, consider the more general equation. we'll, at least for this class, we'll start off including the entire real line, if this is a 1D partial differential equation. So this means that x ranges from negative infinity to infinity. When we have this case, the assumed boundary conditions are that u at negative infinity and positive infinity are equal to 0, and then all its derivatives. So the partial of u with respect to x at negative infinity would be equal to 0 as well. That would be the assumed boundary conditions for that. I won't get into, this is more just for posterity, having these properties of the diffusion equation. It's not going to be too important to our discussion here. But I want to get into an example. So trying to tie things together here. So going back to the ODE example. All right, so we had this ODE, and we had y primed minus ay is equal to this function, right? And so we got this kernel, right? And I didn't really call it that, but this is the kernel that we're talking about. So this kernel then shows up here and here. And so the one I want to focus on is this one right here. So if we look at the diffusion equation without any driving function, the right-hand side is equal to 0. We're looking at this homogeneous solution. And we got a kernel, which is e to the at, and that comes directly from the form of the ODE. You see a is here, right? Okay, so the same thing happens if you want to look at general solutions to the diffusion equation for PDEs. Let's just assume that this is a solution. This is cherry-picked because mathematicians hundreds of years ago have said this is the kernel to the diffusion equation right here. But this is going to be our kernel. We're going to say, all right, does this solve our differential equation? And I wanted to go through and just show that this, in fact, does. So our kernel, we're going to say, is this exponential term here. So you see a lot of similarity. Just like in ODE, you have terms in the exponential. Here we're going to have it as well, where we also have coefficients are included in this kernel here. This k term as our coefficient, or diffusivity of our diffusion equation. So the question is, does this satisfy the PDE? So if we look at our PDE for the diffusion equation, that is ut minus k u x is equal, double x is equal to 0. All right. So if we look at partial of u with respect to t, all right, so this is going to require, well, this is going to require using just the chain rule, right? So we see that we have t in the denominator here, right? So then if we look at this being the first part using our chain rule, we're going to get negative 1/2 because t is raised to the negative 1/2 power. Right, now t is a negative 3/2 power, and then we have our integral. All right, and now we have the second part of the chain rule, which is considering the fact that t is in this term inside the integral, and this is going to give us the coefficient out front. Okay, so this would be the partial of u with respect to t. So it turns into two terms here. Partial of this function with respect to x, we only see x in one location right here. So this is going to be a little bit simpler to evaluate. give everyone some time so people are still writing, so I'll pause for a second. Yes?
Is kernel just a synonym for like a general solution? Like what exactly do
Yeah.
you mean by it?
So, yeah, that's getting into terminology. I don't know if I have the historical background to really say that, but oftentimes when we look at, we'll get into more into convolution. And some examples, we often talk about the convolution kernel, which is synonymous with what's called the impulse response, for those of you who've taken systems classes before. Our kernel impulse response, same idea. I would say that kernel is a more general term than impulse response. So we're talking about solutions to differential equations. It has an impulse response. If I were to turn this term here into impulse function, right, I can solve the impulse response. And so this solution here is the impulse response. I'm sorry, you can't see what I'm doing there. This is the impulse response of the diffusion equation. Okay. So kernel would be more general, especially if you get into computer science, digital signal processing. They often look at convolution of a function, like say filtering. You say you have a raw signal and you want to then filter it. That's usually seen as convolution of that raw signal with what's called the convolution kernel to then get the filtered signal. And so it's basically it's the other part of the convolution integral besides the signal you're trying to filter, what we call the kernel. So it's more general the impulse response, but in this case, it's the impulse response.
And PDEs is impulse. Is this still like only confined to time or is it like space component?
Yeah, so sorry, maybe my drawing wasn't too clear. I'll start over here. So the impulse function is in space-time.
Okay.
Right? Yeah. So if we look at like your standard, we usually think of the impulse function in time, right? Which is this, right? So you may have learned this in undergrad or even in graduate classes, like a top hat signal, where this is going to infinity, and then the width is going to 1 over infinity, right? So the actual real function of this is an exponential function. So then in space-time, it's in 2 dimensions. Yeah. So just make that clear, this would be x, this would be t. Okay. So this is the partial of u with respect to t, partial of u with respect to x. All right, so that's the first time we do this. We do this again, right? So if we want to get second partial of u with respect to x, that's u sub double x. And then I'd have to double check what oh yeah, I see. Okay. Yeah, that's correct. Okay. So the main thing I want to show here, and going through the solution is what we have. I go to UT, right? So UT is composed of two different terms. The first term in the coefficient is t to the negative 3 halves out front, and then our kind of our basic form of our convolution kernel. Second term has t to the negative 5 halves, actually, right? So you have t squared, and you have t here. Make sure that's correct. Yeah, 5 halves. And then it has x minus y squared, and then their regular convolution kernel. So that's ut. If I look at ux, keep in mind that we are looking at does ut minus ku xx equal to 0. We have the same terms, right? So we have t to the negative 5 halves here. We have, let me make sure this is clear, this is extended. T to the negative 3 halves here. This one has x minus y squared here. And then this is all multiplied by k. So one of these k's cancels out, one of these k's cancels out. And if we were to plug all this in, we would see that this, at least the PDE portion of this, is satisfied. Okay? So in terms of this fairly complex function being a solution to the diffusion equation, this satisfies this. And we can just figure this out by plugging it in and see if it works. And I don't know how the mathematicians originally figured this out, 300, 400 years ago, but it works. So why this is a convolution kernel. The other thing we have to do is make sure it satisfies the initial conditions. I'm actually not going to go through this because it's a lot of, it's in the notes. It's a lot of calculus to show that this satisfies the initial conditions. One way which you can look at this is, well, I don't know if I want to go there. It's a decent amount of calculus. I don't think it's too important. I think the main thing is that this has been established that this satisfies the initial conditions for the diffusion equation. I think in the last 5 minutes would be better off for me just to get into an example with this. Maybe I got a little bit ahead of myself saying that this is the kernel. Looks very similar to the kernel solution for ODEs, where we have this general kernel. So the difference between what I showed before is that this has now an integrating, this is missing its integrating factor. I'll show you how this is plugged back in a second, but this is somewhat similar to an ODE case, and it has this term. It just has an extra term out front, which also has t in it, which is part of the argument of the solution. This is a special function for solving the diffusion PDE called Green's functions for diffusion. So those of you taking a PDE class, you may have heard of Green's functions before. A lot of the really basic solutions to additive manufacturing problems use Green's functions to do this. And that's why we're going through this. So I want to point out Green's functions. This is the Green function for diffusion. If you go on the Wikipedia site for Green's function, you'll find the forms for basically all the different types of classes of PDEs. Every single PDE has a slightly different Green's function, which is essentially the solution to the infinite domain PDE. It has some properties. If you integrate the Green's function between infinity and negative infinity, it equals to 1. And if you go just from 0 to infinity, the integral is equal to 1/2. All right, and then here's what the Green's function looks like. So this is a function of both space and time. So it's a little bit difficult to kind of communicate. Actually, kind of wish I would make it. I haven't made a video of this one. Maybe I should. But if we look at this function here, we see that t is in the denominator of the coefficient out front. It's also in the denominator of what's in the exponent of the exponential. So you evaluate this as t goes to 0, this becomes an infinitely large impulse function. So as t goes to 0, this spike is infinitely large. This width becomes infinitesimally narrow. As time gets larger, then you see then the spread of what's essentially a Gaussian function spreading out here. And this is, so just to kind of note, this is just an example for k is equal to 1. Here's our x values, and then these are the different level sets of time, in case that wasn't clear here. So imagine this in time. Maybe I'll make a video for this by next class, and we'll go through it at the beginning of class. Imagine this in time, really large spike, very narrow width. As time gets larger, the height of this Gaussian decreases, the width increases. Or if you look at it in terms of normal distributions, the height of that distribution decreases, the variance of the distribution increases as well. Or height decreases, variance increases. Right. Any questions about that idea? Okay. All right. So I think I have enough time just to barely start this problem. Okay, so the beginning will look a lot like problems like this. And this is, we're starting to get into ideas of heat transfer, which is basically based off the diffusion equation. And so, yeah, I think I have only time to really set up this problem. I don't have time to solve it. But here's the basic scenario here. We have an infinite rod. An infinite rod doesn't exist, but basically we have some sort of medium that conducts heat, and this has, actually I should probably change that. The better term is probably diffusivity of K of this infinite rod. And it has an initial temperature profile where, just for the sake of the argument, just say everything is at 0 except for this region between negative L and L. So somehow you got this rod, everything is extremely cold, and this goes on to infinity in each direction except for the middle, which in normalized form is initially set at 1 between negative L and L. All right, and from this initial condition, we wanted to determine what is the temperature in this rod for all time going forward, being then time greater than or equal to 0. Okay, so the way in which we're going to do this is we're going to say, we know that this is a diffusion equation, so we're looking to solve this PDE. Okay, so this is our PDE. We have initial conditions. So this would be u of x0 is equal to phi of x. And so then this phi of x is equal to 1 for absolute value of x less than or equal to L, and it's equal to 0 for absolute value of x greater than L. All right. So then, beginning of Monday's class, we'll solve this PDE. From here, we're going to extend this, just to kind of foreshadow where we're going with this. we're going to extend this problem into the half space. Maybe I'll just highlight this. Okay, let's see. The half space. So if we have a rod with insulation on one end, okay, and then from there we're going to look at, instead of having initial conditions, we're going to look at what happens if we have an impulse of energy at some point along this rod. And so that is going to be very similar to additive manufacturing problems, which we have impulses of energy, either from laser sources or electron beam sources. We have some cases where it looks like boundary conditions where we have a temperature, that'd be like in the case of material extrusion with heated nozzles, that looks like a boundary condition at a certain temperature. So we're going to start to extend these ideas into problems that look more like additive manufacturing. Any questions on this? All right. The homework problems are getting into some of these PDEs. So some of the PDE problems we don't have enough in the lectures to get through yet, but I think the first problem in the homework set is all material that we covered in the first lecture. So you're good to go on that one. Okay. See you on Monday then.